So let's talk about a piece of engineering that's, well, it's kind of a paradox. It's a boiler that powers our modern world, but its true genius lies in its ability to make steam without ever actually boiling. Sounds impossible, right?
To really get why that's such a big deal, you have to rewind the clock, back to a time when making power was a seriously dangerous business, filled with the constant threat of, you guessed it, catastrophic explosions.
All right, let's set the scene. We're in the early 20th century. Industry is booming, cities are growing, but all of it is running on a technology that could, and very often did, fail in the most spectacular and deadly way possible.
I mean, steam was the lifeblood of everything. It was in the factories, the ships, the power plants. But the problem wasn't the steam itself. The problem was how they were making it. There was a fatal flaw baked right into the process. Okay, so meet the villain of our story, the boiler drum. In a typical old-school boiler, this was a massive steel tank where water was boiled like crazy. Think of a pot on your stove, but make it the size of a car and put it under hundreds of times normal atmospheric pressure. All that violent bubbling created unbelievable stress, and those old riveted seams, they were the weak point. When one let go, the result wasn't just a leak, it was an absolute disaster.
And this is where our hero, an engineer named Mark Benson, enters the story. In 1922, he had this totally radical idea. He didn't just want to build a stronger drum. He wanted to get rid of it completely by totally rethinking the physics of water.
This was the question he asked, and it sounds kind of nuts, doesn't it? How do you get steam from water without all the bubbles and the chaos of boiling? Well, the answer was to push water past a point anyone thought was practical. Benson's idea was to use what we call supercritical pressure. Now, stick with me here. If you put water under an insane amount of pressure, we're talking over 225 times the air pressure around you right now, and then heat it up, something magical happens. It enters this weird in-between state where it's not really a liquid and it's not really a gas. The line between them just disappears. So here's the kicker. In this supercritical state, water just flashes instantly into steam. There's no violent bubbling, no chaotic separation. You get all the power of steam with none of the drama. And if you don't have boiling, guess what you don't need? A big, heavy, dangerous drum to contain it. Boom, problem solved. Okay, so that science is incredibly cool, but how do you actually turn that concept into a working machine? Well, let's take a look at the actual design, because it's just as brilliant. The beauty of it is its simplicity. It's called a once-through boiler, and that's literally what it is. Water gets pumped in one end, it takes a single trip through a long, continuous maze of tubes where it gets heated, and it comes out the other end as superheated steam. It's just one long, uninterrupted path. And when you put the two designs side by side, the difference is it's night and day. On the one hand, you have the old way, big, heavy, complicated, and frankly, a ticking time bomb. On the other hand, you have the Benson design, no drum, a simple system of pipes, and an inherently, fundamentally safer design. But look, getting rid of the drum was the first big win. The real genius of the Benson boiler, the thing that makes it not just safe but incredibly efficient, is how it solves a hidden and really complex challenge going on deep inside those pipes. See, inside any boiler tube, the transition from water to steam is a mess. It's not a clean switch. You get little bubbles, then those bubbles form bigger pockets called slugs, and eventually it turns into a fine mist. Trying to precisely control that chaotic process is a huge engineering headache. Now, here's where it gets even trickier. In a Benson boiler, that exact spot where the last little bit of water becomes steam, it isn't fixed. It's constantly moving. If the power plant needs to ramp up production, that point slides up the tube. If demand drops, it slides back down. You're trying to control a moving target. So how in the world do you do that? Well, engineers had to get really clever. They started to model the tube as two distinct sections. You have the first section with the water-steam mixture and the second with pure superheated steam. And separating them is this invisible, moving boundary. The whole challenge became predicting exactly where that boundary was in real time. And this is where the real magic happens. The solution was math, incredibly advanced mathematical models. As you can see from these charts, the simpler models, those are the dashed lines, they get you in the ballpark, but the sophisticated dynamic models that can actually calculate that sliding boundary, the solid lines, they are way more accurate.
And that accuracy gives you perfect control, which lets you squeeze every last drop of efficiency out of the boiler and makes it incredibly responsive to changes in power demand.
So, what's the end result of all this innovation over the last century? Well, it's a technology that didn't just solve a deadly problem. It went on to become an absolute cornerstone of modern power generation all over the world. I mean, the advantages were just a total game changer. It's safer, period. No drum, no main cause of those explosions. It's much more efficient. It's about 20% lighter, which makes it cheaper to build. It can be fired up in just 15 minutes. And as we just saw, it's a master at handling the constant ups and downs of a modern power grid.
The numbers really do speak for themselves. More than 1,000 of these have been built, making the Benson design the most popular once-through boiler in the world. Mark Benson's idea didn't just work, it completely took over.
And this technology has never stopped evolving. From the original patent in 1922, it took only 5 years for the first industrial one to be up and running. By the 1950s, it was already pushing the limits of supercritical pressure, and it's still being adopted for new technologies even today. And that just leaves you with this one final thought, right? How can an idea from 1922 still be the beating heart of our most advanced, high-efficiency power plants a whole century later? I think it just goes to show that sometimes the most genius solution isn't about fighting a problem head-on, but about finding an elegant way to avoid it altogether.